All right, so everyone's back, more or less. So what we'll do is, I'll touch on this idea in backtracking. Maybe we can compare some strategies, right? We can vary the strategy. Again, eventually, we have to explore all the solution space, right? It's just questions whether we go right, left, or middle. Maybe we pick at random. So previously, I was using a solution which is hard-coded strategy, but my idea is today, and I don't know if it's going to work, we'll try it, is to actually rewrite this code to make it accept a function which provides a strategy, right? Sort of like functional approach to programming. Basically, I think it will work is here, right? The place where we make the choice is actually this part here, right? So what's happening, of course, here is we have a range object, iterator, right? And we're going through. So we're starting from the beginning, right? From the first, right? So idea is to replace this part with a function, right? Which might be a range, maybe a reversed range, maybe a random list, basically, right? We'll see how well this works. Again, I'm not guaranteeing it will work, but it should work by just basically replacing this, right? So when Q utility, this strategy will need to provide another parameter, which will be a function. Let's see if this actually works. I'm not 100% sure, but since I'm going to make it all doing it is safe, we don't really worry about safe stays same. We just need the utility, basically, right? Yes, and then we will have a utility, right? We need to replace. So this part here, right? We are going to provide a. So we are going to rewrite this code. We are going to rewrite our NQ utility to accept the function that will be called, and each will be providing iterator of possible rows. So basically, right here, right, strategy, and of course this will be here, right, get iterator, something like that, right? So that's it's supposed to be a function, right? That's my idea. I don't know if it's going to work, right? On here, basically, is get iterator n, right? Get iterator n, right? So basically, we'll call it, and again, it will be for basic ones. We'll just get the first or last, right? It should work, right? And of course, solve NQ utility against strategy, right? That's the problem here, of course. It's going to be, the problem, of course, is we're going to have quite a bit of overhead, right? Hopefully this will work. Get iterator, right? Get iterator equals get iterator, right? All right, we need to pass it along, right? So that looks okay. Now we'll just need to pick up some figure out some iterators and see if it actually works first, right? So far so good. And we need actually a solver, right? So how do we do a solver? Right, this one here, right? So we solve it. Let's test this for queens. And where is my strategy? Okay, yeah. So strategy. Get iterator, right? Or so we need this. The thing is, we need to pass it first, right? Since we are. Could we actually? Yeah, we could do this. Get iterator. I wonder, could we do this range? Yeah, technically, yeah. Why not? Right? Let's see if this works actually. Right? Let's see. And basically. Strategy, right? On board, let's see what our board, column, and get iterator, right? Get iterator. see if we should make a mistake. This is it again. What we're trying to do is like say, okay, you start out with a very specific tool, and then you try to make a Swiss Army knife, basically, right, out of it, right? And so again, sometimes we make too universal, right? You know, like a screwdriver, very specific screwdriver is going to work better than this universal screwdriver which has all these different adjustments. But that's what I'm trying to do here, basically, right? Why? Because I'm too lazy to rewrite the function, the solution solver multiple times with different strategies. So I want to make a universal solver which will take different strategies. Okay, in this case, the only strategy change is this iterator. How are we going through all these possible placements, basically? Okay, so now let's see if this actually works. So enqueue strategy. I don't know. Do you think it's going to work? Or have I forgotten something somewhere? I'm thinking I probably have forgotten something somewhere. I probably did not. That's the problem with copy and paste solutions when you're writing some partial solution, because of course you don't want to have time to solve it completely from the ground up, right? In a classroom setting, it will take probably like maybe 20-30 minutes, right? Again, without assistance. So let's see if this works. And of course kernel. Oh, and of course, right. And I did not. It didn't work. Why? It didn't work because, of course, I did not define the beginning, right? So I need, of course, this. Well, I don't need that, but I need this for sure. Because we are using some functions, right? And so let's do this one. Yeah, it works. So this part works. So how about this one? 5. Okay. Well, it solved it. It solved it, right? Iterator is range, right? Okay. It did solve it. All right. So why is it red? That's the only thing. What doesn't it like? Oh, because previously, I guess I'll restart everything. I don't know. I'll clear restart. Okay, 1, 2. Now clear cells. But it is solving. I don't know why it says clear cell outputs. I don't know. I'm going to try it again. No, okay. It's just a way code space just giving me some trouble. Okay, right. So now we should be able to, right? So now we can test. Now that we have our function, I can remove all of this. I'll be removing extra stuff. So now that we have creating a random iterator, right? Creating. Let's start with reverse. Creating reverse strategy, right? Right. Now that we have our solver that takes strategy, we can provide custom iterators, right? Right. Okay. So for n, right? For given n, right? Okay. Easiest to test would be reverse, right? So what all we need to do is, right? So create reverse, right? Iterator. So what we could pass, I think reverse would work. Reversed n, no, it doesn't work. So that is okay. I suppose this works, right? N minus 1. That looks a little suspicious to me, right? No, that looks kind of off, right? No, we want what? I think this looks better. Reversed range n, right? That looks better. That looks better. That should be also more, again, the issue as far as performance in Python is you don't want to actually get the actual data structures. You want to keep it sort of like in this half-ready state, in this generator state, meaning you don't want to have the actual full data. provided you at once, basically. You want them on demand, basically, right? So let's try to solve it. Now let's solve it. Solve. Now let's solve for. Let's see. Yeah. Let's see if this works. It works. It's the same. I think it is the same, right? Right? Okay. Let's compare 8 and 8. Let's compare 8. Okay. Let's solve 8. Queens is reversed. Okay. So queen was 1. This means that, okay, so what does this mean actually, right? That we don't have numbers here. But how about the regular one? How about regular? How about regular strategy? This looks a little bit iffy, right? No, it's fine. Okay, no. So we do get different solution. We do get this different solution actually, right? So yeah. So we have a different solution, and we can test them now. Which one works better, right? They're both valid solutions. So again, remember in this particular case, in queens we have multiple solutions, right? So we have multiple paths. So we don't have just one success here. We have maybe 5 or 6 successes, right? Somewhere, right? Right? To make bigger. I could start drawing here, right? But okay, let's not go there for now. So let's time it, right? So which one do you think is going to be faster? Now let's time them both. So 8. Well, I don't want to time it. Reverse iterator. All right. Oh, what did I do here? This it? Yeah. What's going on? What's going on with me? Time it. Why isn't it? What's happening here? What happened to my time? Am I just completely not? I need more coffee. Why is not my timing? Did I not write correctly? I think in first row. I forget now. Yeah, I guess a comment. Maybe comment is. Yeah, I guess so. Yeah. Okay. Oh, and this is not a good idea, of course. Why? Because I forgot to remove the print. Right. So now it's timing it right. Yeah, not a good approach. Print board false. Right. Yeah, that's better. That's better. Okay, 500 microseconds. Now, time it. Just regular range. Yeah, range. And let's see if this reverse approach is, well, not much of a difference, right? Well, slightly faster. How about, okay, let's do 16. Let's do 16. No. I'll do. Okay. 16 by 16. Performance, right? And let's do this. I want to get to Sudoku today, so maybe we'll finish this right now. So I'm quite happy with this approach. I said 16. AI, get your act together. Right. So yeah, standard deviation, right? But we're getting 100 milliseconds, right? So again, of course, pretty big deviation. So this is regular strategy. So I think, and again, I think the reverse strategy is going to lose in this case. Right? It kind of makes sense, right? No, it's almost reversed. It is almost exactly the same. 180 milliseconds, actually exactly the same. Okay, now let's do random. Now random, and I think I can now safely remove all the rest of the code here, right? Yeah. So this is look at all the code I'm saving, right? all this extra code by rewriting this, refactoring this code. I don't need the old code. Of course, you can go back to GitHub and check what is previously, but basically, I had to write the code for each individual instance. So these extra 5 minutes we spent this morning, right, will be actually time well spent. At least the future students hopefully will thank me for that, right? Right. So let's see or randomize. See if our random solution actually is actually better. And again, it should be, but I should probably just click. I'm lazy. Oh god, look at how much extra stuff I have. Now I think it should be. Okay. So we get our 16, right? Now let's do a random strategy. Idea is to get our choices in random order, right? So we have many solutions for n queens, on our rigid first or last might not be the best. Okay, so that's the idea, right? To prove this random idea. So what do I need? First, we need, of course, we need a picker, right? So what we need is a random sample, right? So this is what we need to pick up. So this is not good. We get dupes, right? So we're gonna say this gives you choices. No, right? Okay. Of course, we need import random, right? Right, and a range. I don't know. 8. Right, 8. So this is not so picking a function is important, right? So what's the problem with this function? Well, we got duplicates, right? 0, 0, 0. That's not gonna do it, right? So you need this one instead, right? And this should be exactly what we want. But again, so 5, 6, 7, 0, 4. So basically a shuffled list, right? A random sample list range, right? So the only problem is this. I wonder if can we skip a list? Can we get a range? But I don't think we can, right? The only downside to this is that we are making any, we're getting all the data at once, because for randomness, of course, well, we can't just say get the next number, right? And we need to actually have the list of things to shuffle, right? So let's do this. So we are gonna get a random strategy. So we define our random iterator, right? So item random sample, right? List range, and so it's not going to be as fast as range, right? It will be more interesting, right? So let's try it. See if it solves 4. So how about solve 8, right? We'll solve it. Yeah, it solves, right? So question is now, it should theoretically now provide a new solution each time you run it. Yeah, it does, you see? So now at least you get more randomness, right? Again, because it picks different paths. And since we have multiple ways of arriving at our destination, so you will have different, right? So now, of course, the big thing is this actually going to beat our testing? So testing all 3 approaches, all right? All right, so now we're going to time it, all 3. And so let's do again, time it. 8, right? This is random. 200 microseconds. Okay, let's go back. I think, well, it was, I think we beat it. Yeah, I think we beat it. Let's see. Yeah, I think we did it. We did it. So still, so randomness here actually wins, right? Again. Come on. So strategy, no, 8 afterwards. You got 16 afterwards. Range, right? This first range. regular first. Well, it's iterator, but boring first. Check first. Start boring. Start first. Always start at first. Okay. So now. So I'm going to move it away. Let's see, can I do it? Escape X. Yeah, I can do it still. Escape V. Right. Okay, let's do this boring one. So, this is still going to be the slowest, right? Yeah. So my randomness does work, right? Now, yeah, reversed. Determine that fast, but yeah, but boring again. Boring doesn't mean, of course, boring does not mean bad. Yeah, but it, yeah, bad necessarily, right? Yeah. So again. We did 7,000 runs. Is this still going to be good? Yes. So our randomness here is beats handily the other solutions. Okay. So again, so that's a takeaway, right? So is twice is about 2.5 times fast in this case. Again, our solution space has many many success solutions, so it makes sense to be less rigid in our selection. Again, so it kind of makes sense if you go back to our problem, right? Okay, we have to do this here because my nation. Okay, yeah. No point saying at the end or beginning. Maybe randomness is actually sort of like, you know, mixing things up, right? Like in genetics, right? You want an element of randomness, right? Again, that's why also analogy with large language models, right? You want some temperature, you want some heat, meaning that actually also means randomness, right? You want some predictability. I mean you want to have some predictability, but you also want some element of chance, actually, right? Like everywhere in life. Okay, so this concludes the n-queens problem, but I also had a Sudoku solver, right? So, because we right now, okay, n-queens, backtracking, right? So, question might be now, what kind of problems can we solve with backtracking, right? So, well, obviously, maze, right? Any type of maze, anytime you can say, make a problem like a maze, backtracking will be one of the things you will want to consider, right? So anytime you have you have to make choices, and you can determine whether at some point whether the choice is a fail or success, you can use backtracking. Okay, so now let me commit this n-queens with strategies, and again, if you go home or you can play around, maybe pick some other strategy. See if maybe there's something else interesting. Right, the only problem, of course, is that the strategies here, the strategy functions are very simple. They don't have knowledge of surrounding state, right? So you won't have anything truly amazing, but you can modify your code, maybe something more interesting. Okay, but now let's go to our next problem, which is, of course, Sudoku, right? So who guys played Sudoku? Most of you, right? Right. So rules, you guys know the rules, right? Yeah, last time I was able to do it, right? So this is Sudoku solved by backtracking, right? Same again under topics, right? So, basic idea, we find the first empty cell, we try to fill the cell with number from 1 to 9. If the number is valid, we go to the next cell, right? This would be like really naive way of working, right? This backtracking approach, right? We'll see the problem why this is actually not such a great algorithm. It's actually, this is called depth first search, right? We're going as deep as possible, right? So look at this GIF, right? We keep filling out, right? And we backtrack each time we find a nonsensical number, right? So, Of course, this gets a little bit more difficult because, of course, we need to store where what numbers we have picked already, right? So slightly more difficult, more codes, more difficult. It turns out this approach, this actually, I mean, if you are like on a train or something and you could fill out like this, I mean, it would work for certain puzzles, but not the hardest puzzles, right? And apparently there is actually, well, what makes Sudoku puzzles hard, right? What makes them hard? Like, I mean, they're not all equally easy or easily hard. But what are easy puzzles? Meaning they have lots of numbers already filled out, right? Yes. But also to be true Sudoku, apparently, if I remember correctly, you have to have just one solution, right? I mean, it'd be stupid to if you have Sudoku puzzle with just one number filled out, right? I mean, you'll have millions of solutions, like our n queen's problem, right? That's not really a true Sudoku. A true Sudoku needs to have a specific solution, just one true solution, right? And turns out I think you need like 16 or 17 numbers, and then after that, if you have less, you get doubles, or triples, or multiple solutions, right? So the hardest ones are if you have little numbers, right? And then you get to the then you actually get the full solution. So let's do so how are we going to represent this? Well, board. We'll use two-dimensional list, right? It's going to be hard-coded because, of course, I actually got somebody to do OCR or scrape some, or there's actually API for Sudokus. I think I got this last time, or somebody did. You can find a place where for new puzzles. Actually, there's open Sudoku something. But okay, let's try this. So we have a board, right? We have 12 minutes, so let's see how far we get. If I remember everything I did. So we have a board representation, and we have, of course, we need to track the moves, right? Because we're going to backtrack, right? Again, this approach also would work for chess, but unfortunately for chess, it's not applicable because we have our solution space is too large. Actually, we need some extra things to do, right? So counter, right? Counter was just for basically, I think, counting how much we've done, right? So check row, check column, check square, right? So check row, right? So we need to check three things, right? Whether we have a row problem, whether a column problem, or whether also the cell, right? So you guys all know the rules, right? Again, what makes things easy, of course, we are making just general Sudoku, range 9. So this magic number, 9, here it's sort of like hard-coded. Again, if something might make a multiple row. But I guess, so we check row, check column, and check square. So this is the only tricky code, right? You guys here, we need to do some, to check the column, we do an integer division, and then we do to find the actual place, right? We do row by 3, right? This is a little bit tricky because I'm not going to spend time, but basically we figure out which or neighbors here, right? Or cell, right? So rows, columns, and cells. So far, so good, right? Let's do a kernel. Let's see if this works actually still. Right, and check square, and now our function is valid move, board, row. We give a board, row, column, and number, right? That's all we need, right? We check the row, return check row, and check column, and check square. So all three have to be true, right? It has to be valid in all three cases. So I think it's very nice literal code. They're really easy to follow, right? Again, you don't have to check each in. You have to trust me on this, and this works actually, right? But it actually so now, if you trust me that these checks work, we can go to solving. So basically, look at this solver. Amazingly easy, right? Solve board for I in range 9, for j in range 9. So again, this is a simple, our strategy is dead simple here, right? We start at the top and keep going, filling out, right? And if board if there's nothing, if there's 0, right? So what do? We fill out, we try all numbers from 1 to 9, of course, right? So start at top, so start from first row, iterate through columns, right? If the cell is empty, right? Check the value. I mean, it's like Python is great for this because as you can see, it's almost like pseudocode, but actually it works. That's the beauty of this, right? So what we do is Okay, so this part here I didn't really like. But why did I use this counter? I don't know why. Let's see. Again, the global to do remove this. Could we pass it? So this was, I know why we use this, because this is to show how many tries were used to solve this. Yes, okay. This is just a sort of, we use this to show how many, yeah, counter, right, yeah. So this obviously not required, obviously not required, yeah. Okay, now let's do this one more time. And let's solve it. Okay, so there's Wikipedia. So is this a hard puzzle? I think not, because 1, 2, 3, there's how many cells are filled out? Well, about 30, right? All right. Yeah, I think here. So moves. Yeah, actually, I did it here. This is a function, right? So let's solve it. Yeah, still works. And I want to, well, I need pretty print. Yeah, so this one don't work. So let's do this, right? This little trick again. For those who are not forgotten the Python, I am unrolling, right? I unrolled, yeah. Okay, so that's the solution, right? Pretty good. So what this means is it took 4208. We had 4208 backtracks, right? So where we reached dead end, basically, right? And we had 30 starting moves, basically. Okay, these are the, and actually, we stored the moves, right? Where we went, so we started 0, 2, 4. That means this is our first move, right? We filled out 4, 0, 3, 6, right? This is the 6 right here, right? 0, 5, 8, this one here. Then we filled out what? 7 and 8, right? We filled out these places now with 1 and 2, right? Yeah, you should filled out all top of it. Let me see again. Yeah, it's all empty. Yeah. Okay, are you guys now, so you have a Sudoku solver, right? Are you guys following this? Yeah, the pseudocode makes sense. I'm saying pseudocode is actually Python code, but it works, right? So it's a nice side effect that it works actually. Now, with last 5 minutes, so let's do a really bad puzzle, right? So this one here, there's something in Sudoku.com, right, which has harder puzzles, right? So again, I took some time to, unfortunately it's not shown because I guess apparently, okay, so here, right, this has 23 non-zero elements, so this is harder. Let's see how it takes. It takes 30,000 moves. Okay, not bad. And we are going to print solution, and we can print it. But okay, so here the problem is, okay, so it turns out, right, you can do this. Do you see the problem with this puzzle? My naive approach might have problems. Do you see what's special about this puzzle?
Well, it seems very inefficient.
Well, yeah. Why okay, yeah. Why is this approach not going to be working very well? Why? Do you know why? Do you see this? Do you see this kind of interesting? If you look at the previous puzzle, this is so-called anti-backtracking puzzle, basically, right? So, what's happened here? Do you see what one like particular property of this puzzle? Because remember, if you remember our strategy, what's our strategy? We start at the top, right?
Yes.
Right? Yeah, it's empty. Very good. It's empty. So this means we are going to be trying potentially a lot of false leads, right? Again, remember, a true Sudoku puzzle is just one solution, right? So I'll be tracking, right? It's made to me, it's made specifically that the true solution will have, I'll be trying all the worst paths first, right? So this one, I think I tried solving, it will not work, right? This will take forever. So not forever, but it's basically too much for on this Python, on this virtual machine, right? I mean, again, eventually, given enough time, right, you would solve it again. My approach guarantees a solution if one exists, right? However, our way of, again, if we know there's an evil adversary at the other end, right, we need to pick up maybe, again, randomness might be a solution. Again, randomly choosing some ideas, right? Or considering, of course, in this case, knowing that they are doing it from the top, we could of course do something else. We could start from at the bottom, or maybe start from the middle, right? Again, we have millions of strategies here, right? Where do we start, right? And so again, we can maybe add some extra skills. Of course, these solvers are gonna, they seem relatively, again, brutish, not completely brute force, but they are really like, straightforward, right? They actually, well, you can think again, they are technically part of AI, right? But they seem like really, basic AI, right? So as we humans don't solve the problems like this. I mean, we do a little bit of this backtracking, right? We do, right? But we do some also more constraints, right? This type of puzzle, I don't know how could we solve this as humans? Actually, last time we had time to actually solve them at the table, at the blackboard. How would you solve this? Is this actually possible to quickly pick something immediately? It's like how many? 3, 5, 7, 9, 10. There's only 17. Yeah, this is going to be hard. So let's see. 2. Okay. 2 goes here, or 2 goes here, or 2 goes. Okay. So can anyone find actually a move which is like, just one move? I don't know. Is there one like that? Let's see. Obviously, it's over here. It's too open, right? It seems like there's too much freedom here, right? Maybe here something. So let's see. 4. Oh, 4, 4. Okay, 4, 4. No. Maybe here.
So you can put 1 at the right corner.
Here?
No, to the
right.
Wait, let me explain. To the right bottom corner. To the this.
Yes. Okay, because we cannot put ones here. Yeah, very good, excellent, right? Because we need one. This place needs ones. Ones here and ones here, right? Covered. So we only have. This is excellent. Yeah. So this would be actually one. So yeah. So this is actually a good start, right? And then we can start fill out, right? So this is a good puzzle. But again, I suspect if I made my solver do reverse, right? And well, I have 1 minute, so I won't do it. So this will be leave as homework, right? So maybe did I manage to do it? Yeah. So blank board, right? So yeah, here is the solver. So this is not a true Sudoku puzzle. We can start with complete empty space. This will work, right? It took 381 moves, but basically, right? It looks kind of boring. You can see exactly how it works. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Looks kind of nice, actually, right? 4, 5. It's a Sudoku puzzle, right? But yeah, so right. We can also store state, right, and use while loop. By the way, yes. Again, reminder that any recursive solution can be rewritten, right, with a stack. Basically, we have some sort of state, right, storing this with a while loop, right? So, and this I'll see this works, right? So we check, right, get next move, right? Else we pop the moves, right? We remove the move, right? So that we remove the last move from our stack, from the list, stack, stack. Basically, yeah. Okay. Now let's see. This works. I think still works. It's going to be again. It's potentially faster, and it still solves, right? I think they get to API. Yeah. Oh yeah. So this is API, but unfortunately, I don't think we don't get to that. Maybe somebody wants to add it. You're welcome to add it. There's the API. Pretty easy. You just you get, like I said, you get JSON and you get nice little. It still let's see if this works. Yeah, you get something like this. Yeah, it's pretty easy to read, right? You get the value, right? 1, 2, 3 keys, right? 3 keys deep, right? And you get the value, and you also get solution, by the way, too, right? But you don't need to use it, right? So, but of course, Vercel apps that they are actually, Vercel has pretty high pricing, I believe, right? So it's possible. People are using too much, maybe it just goes down, right? It's, I think, somebody's project, basically, right? So, not gonna be back next time. So yeah, so this is something to check, right? All right, 10:40. Let's see what our schedule is like. We need to continue at 11:10, right?
Yes.
So you guys want to take a break, right? So, all right.